When we get to the end of the presenter, we will ask individuals who have raised their hands to ask their question, and we will unmute your line. So everybody is muted right now. So let's go ahead and get started. Our first presenter is Karin Wadsack. Karin is a project director at NAU's Center for Engineering, Forestry, and Natural Sciences. Karin manages a number of renewable energy research and energy initiatives and teaches classes on a variety of energy topics. She is a key member of our Four Corners Wind Resource Center, as NAU is one of the 3 partners. She serves as a policy and technical analyst on energy issues at the university and for a variety of entities in the community and across the region. So Karin.
Great, thank you very much, Amanda. And what I'm going to do today is just briefly show our attendees some of the excellent information that our Four Corners Wind Resource Center has compiled. And then we're going to move on to our other presenters so that they have plenty of time as well. For those of you who don't know exactly who we are, the Four Corners Wind Resource Center is one of 6 centers across the country that's supported by the U.S. Department of Energy in the Wind Exchange Program from the National Renewable Energy Lab. Our mission is to get useful, up-to-date information into the hands of decision makers across all of our territory that we serve. And our center, as Amanda mentioned, is built on the work and part of our member organizations, which include NAU and also Utah Clean Energy and Interwest Energy Alliance. Graham, I am not able to move the slides forward, so if you want to advance those for me, that would be great. And go to the next slide. So here I've listed just our website address and the resource section that we have available. You can find there the latest reports that we have, maps, examples of regulatory documents, and a lot of the other information that we as an organization have found for you, read, and compiled for you to be able to access. And here you can see an example of one of the fact sheets that we've put together for each of the states in our area that we're working in. And these, of course, are also available on the website at the address that you see on the screen. Next slide, Graham. So I'm going to quickly run through one report that I'd like to highlight today, and this is the Wind Technologies Market Report. And it comes out every fall from the Lawrence Berkeley National Laboratory. If you're familiar with this initiative, you've probably already read the report from this year. And if you are not familiar with it, it's one of the resources that I would strongly encourage you to take a look at. Next slide, Graham. And what they do when they're putting this report together at the lab is they come through all the data that they have access to about every wind project that's built each year, and then they compile statistics on the cost, price, location of projects, technology changes, policy drivers, and other factors that are influencing the market. And then they add the information that they get from this year to all of the data they've previously compiled from all of the years leading up to this year, and that way they're able to characterize the current status of the industry as well as historical and expected trends. And then they put together excellent graphs and charts that they use to illustrate the information in the report, and I'm just going to walk us through a couple of those. Next slide, Graham. So here you can see a plot of the annual and cumulative installed wind capacity in the U.S. And you can see the growth in the industry as well as the influence of things like the general health of the economy, in 2008, 9, and 10, and then also policy drivers like the production tax credit, which is where you can see cliffs falling off in development there. Graham, next slide. And then this plot is showing the trends in wind turbine size and capacity, and you can see that there's an overall trend in increasing component size, but rotor diameter actually continues a recent increase while hub height and nameplate turbine capacity have been leveling off. So that can lead to projects that have higher capacity factor or can generate economic wind energy, even places with a lower wind speed regime. Next slide, Graham. And as I think we all know, installed project costs have continued to decline, and that's just what this is showing as the trend over time. Next slide. So project costs coming down obviously results also in potential decrease in PPA prices. And so what we're seeing here is the price that wind is actually sold for, the national average, as well as the variation in prices by region. And you can see clearly that across all of the regions, prices have been coming down significantly since 2009. And the average PPA price across all projects for the last 2 years has been well below $30 a megawatt hour. Next slide. This report also compares wind's outlook to that of generic wholesale power as well as projections for natural gas. And so using information from the power purchase agreements that were signed in 2013 and 14, you can see here the authors are able to show that wind is going to continue to be competitive and is competitive with natural gas under all of the scenarios that have been projected by the U.S. Energy Information Administration in their annual energy outlook. That is the gray and black that you see as a higher price than wind there. And I would expect to see the same or better for contracts signed this year or next year. Next slide. And the last piece of information I wanted to show you, the folks who put this report together also compiled projections for a range of other studies that are focused on this topic. And their conclusion in this year's report was that strong performance is still expected in 2015 and 16. And as always, it's hard to predict the rest of the future. So if you have any questions specifically for me, I'd be happy to take them at the end of our time today. And otherwise, I think we're passing the mic back over. Thank you.
Thank you, Karin. So we are now going to move to our second presenter. We've got Mark Rush with us, and he's from General Electric, where he's serving as the Technical Director for Renewable Energy Sales, and he's been there since about 2010. Prior to joining GE, Mark was the Vice President of Program Development at Vestas America, and he spent 12 years in telecom at Lucent Technologies. He also was a private developer in a previous life in Panama and Colorado for 5 years, and he lived off-grid in Bocas del Toro, Panama from 2004 to 2008. He has a master's degree in international management from Thunderbird, a project management degree from the Stevens Institute, and an electrical engineering degree from MSU. So we're really pleased to have Mark with us today to talk a little bit about some of the capabilities of modern wind turbines. Mark.
Hey, Amanda, thank you. Wow, talk about your life summary in 30 seconds or less, but that's definitely been it. And I enjoyed my current life and my previous life. But yeah, so we want to talk about trends in wind, how we can value it, how we can share it with other forms of energy. So first picture, this is northeast Brazil. The trade winds go right past this area. So, one of the biggest wind farm areas in the world is this northeast Brazil area. Let me see if I could change the page here. No, I can't. I'll just say next. It's okay. So we can go to the next page. There we go. All right. So last 10 years or so of sort of GE products. So Karin had talked about hub height as well as rotor. Hub heights, they do go higher occasionally. You want to find higher shear areas for greater hub heights. But, rotors and megawatt ratings, definitely on the way up. Really, the latest products, say 2014 going into 15, we're into rotors at 120. We've got hub heights into the 140 meter range in Europe. Most of our 2023 products, these are more of the North America products that you think of for, Midwest corridor, different places like that. But over the last 10 years, we've seen capacity factors basically double. And these would be gross capacity factors, say in the mid-20s to now up into the mid-50s. You want to take net losses off of your grosses, but basically doubling in capacity factor and doubling in revenue per turbine. So that's what's driving the lowest cost of energy and all the cost curves that Karin had talked about. Next page. So this is kind of looking at what we call constraints versus speed. So in the Americas markets, we typically see megawatt constraints, we call them. Say a 100 megawatt farm, you can put X number of turbines depending on the rating. Where in Europe, it tends to be more land constrained. We have land constrained areas in the U.S. They tend to be more northeast. So this is kind of our index of how we look at different things. Latest North American products are really the ones right there in the center, 20116, 23107. That's really the North America product of choice right now. Next slide. So in terms of evolution of the industry, as I said before, a combination of things have happened. Doubling of capacity factors, bringing availabilities has been a key part. When I started in the industry 7-8 years ago, gearbox problems, lots of machine head type problems, whether they be gearbox or generators, which drove poor availability results. And I've worked with a couple of OEMs, so I know that this is an industry problem. But in the last few years, we're seeing 98% availability, with GE, as well as I'm hearing that the competition is driving similar results. So, well done for the industry. I think we're really getting not only valuable products, but quality products. And that's also helping with cost of energy. If we can have reliable products that our utilities, our developers can depend on, there's a good value there. And then in terms of PPA rates, yeah, we're getting below 3 cents a kilowatt hour kind of range, $30 a megawatt hour. We see that quite a bit. How do we continue to lower costs of wind? Rotors are going to keep getting bigger. So there's physical assets, something like a rotor, something like a taller tower. There's also software, and so you probably can't avoid GE's campaign on, being a software company, and not only being one, but being a top 10 software company. So we're really geared up to blend in even more intelligence into our turbines because we see a lot of values there. Next. In terms of information, so this is an older page, but basically with the SCADA systems, we're getting a huge amount of data flow per second. Lots of sensors all around the turbine, which gives us a lot of loads information, a lot of time and moments information that we can use to perfect how we can push an existing turbine into a higher application space. So we're getting near real-time capabilities to adjust loads and thrust and other items to push some of our existing products into higher envelopes, as well as to bring new rotors into the market and put them into these great application spaces. More AEP, it all translates into lower cost of energy. So next. So as far as wind is a good citizen of the grid. The U.S. we're coming along. I'm sorry. Okay.
You're fine.
So,
you're fine.
Okay, thank you. All right. So for the U.S., we're coming along. Xcel is sort of leading the pack in terms of our utilities of blending wind in. I saw a 61% mark that we hit at some point here in the last 12 to 18 months. I think it was probably 12 months. But if we look to our European friends, Denmark has already done over 100% of their power needs from wind. Portugal, Spain, Germany, they're all doing it. They figured out how to blend in wind and take advantage of free fuel. So how do we do that? We use our weather forecasting systems to understand how our resources coming to us. For the U.S., the weather tends to come in from the west and head to the east. And we actually have very sophisticated models to figure out, what that resource is going to be in the 15, 30 minutes, day ahead, sort of calculating spaces that we need to take advantage of that. We have a sense of what our resource needs are going to be. We have a sense of, what are the resources that are coming our way. And with high capacity factor turbines, when we're getting turbines that are fairly predictable, we have a real sense of how much energy is going to be coming in time. We can really use that to thread into our energy model and blend in as much wind as possible. And some of the European countries are getting very good at that, and we are fast following. Next page. So in terms of plant controls, I was asked to talk about how we can do generation control. So there's a couple of different aspects there. Number one is forecasting. So I talked about predictability of the resources that is coming that way, that is coming our way. How will those resources affect turbine A versus B versus model X versus Y? That's just math. So we can actually do a fairly good job today at short-term predictions. In terms of power controls, so we can look at ramp rate limitations, the governor response, using the inertia in the turbine for things like frequency or voltage controls. We have the capability to overspeed them occasionally if we find some advantage there. So there are any number of curtailment versus regulation methods that we have to control individual wind turbines as well as a wind farm as a common unit. So we have controls at parent or child levels. In terms of voltage controls or frequency controls, we have the same capabilities. We can look at droop compensation, any kind of line drop compensation, plant communications, VARs as they're needed. We have power factor settings that we can apply so that things are responding real time to basically manage a smooth curve. In terms of stabilizing following any disruptions, so we have ride-through capabilities, whether those are high voltage or low voltage ride-through capabilities. And all of those items can be managed not only at a plant level, but they can also be communicated to the grid operator as far as, here are the events, here is the response, here's the expectation. And, I will say the nice thing about General Electric is it's an electric company with a wind option. So they're already very good at this, and now they're actually very good at wind now as well. Next. So predictable power from wind. That's kind of like any renewable energy. That's always been our Achilles heel is, the sun doesn't shine, wind doesn't blow, things like that. Well, we've been using batteries for about 3 years. And by using, I mean, we've actually installed batteries adjacent to wind turbines and been doing field studies for several years now, not only with different battery types, but different configurations. And what we're learning from this is that we can create, in effect, a buffer capacity to make the wind more predictable for, say, a 10, 15, 30-minute period. We have the ability to commit power for different time periods, and we can close down what the standard deviation would be without those plant controls. So there on the right, you're seeing a deviation of 6 positive or negative to a mean. With batteries, we can effectively close that for specified periods. Next. Excuse me. So storage does a couple of things. Not only does it help us with time travel, but it also helps us with smoothing power out. So we can perfect the frequency needs in case there are any adjustments in the grid. We can use batteries to also compensate for that, as well as we can use the batteries with some of the ramp rate controls. As maybe there's a power need on the grid, the wind is down, we have the ability to provide some power while the turbines are coming online, as well as the ability to to smooth in different situations. Next. And I'm saving most of the time, by the way, for questions. So smarter machines, we're all in terms of sensors and software. In the past, we've had pretty good sensors, pretty good model-based controls, but they've all been responding to events. We're now getting better at what we call virtual sensors and smart responses, and those smart responses can be a full shutdown to prevent some extensive damage, let's say, or to make a situation much worse than it otherwise would be. So we're getting much better at that. The future is all about what is the resource coming to us, and so we're using LiDAR and blade sensors to understand the resource that is out in front of us and how we can go ahead and prepare to sort of embrace that resource and maximize that resource. And again, we look at things at an individual turbine level or a turbine as a collective. So again, parent or child responses we find are valuable in different scenarios. Next. So what we're calling our brilliant technology is, again, extending software into this parent-child relationship of wind turbines. So we've got storage capability that can be used with the converter and the controls within the turbines. We have the ability for the turbines to share information, to share, say, what's happening with the front line of a wind farm that's going to be coming through the wind farm, and how that can make a predictable adjustment to the subsequent lines, let's say, of the wind farm in the direction of the prevailing wind. We have the ability to do any kind of controls we need. We can do noise management in terms of adjusting the blades, adjusting the speed to manipulate the acoustic output. If we have a need for time of year or time of day, we can control that at a individual or parent level. Wake management is one of our latest success stories, I guess, and we're talking about as a wind farm, the wind is coming through in a certain direction. That's creating a wake effect through that turbine. We can predict what that wake effect would be, and we can adjust the turbine behavior to maximize the output of the wind farm at all times. So there are some tricks in doing that that we found are beneficial. Next. So sort of putting it all together, you've got integrated data and real-time analytics that are all happening. We've got 28,000 turbines out there, 120 sensors per turbine, 900 signals per turbine per second. So there's a massive amount of data flow that's occurring. We filter that data for what's the material versus the immaterial data. We have algorithms that we can apply to that. We have analytics that can give us sort of a red, yellow, green traditional output, or add a social media element to that. Put it to your smartphone, and you've got you've got some great analytics. You've got some great responsiveness from the people in the field as well as the back office experts. You have the ability to predict that event, what are the possible outcomes of that event, what controls do you apply to minimize the outcome of that event. and then you would modify and adapt your controls for that situation. That's a continuous feedback loop as we learn from, say, one type of farm or one model or vintage or one part of the world or one electrical or grid condition. We're able to tag those and use those to fill our library of lessons learned and responses. So there's a great feedback loop. There's great tools for applying lessons learned. Next. So the digital wind farm is something that we came out with at, I think it was AWEA in May. And so the digital wind farm is sort of putting it all together, putting sensors, intelligence, creating what we call a digital twin. So we have a replica of a wind farm, the models, how that wind farm is built, and then from that we can apply different criteria to that and predict how that wind farm will behave. We can apply loads. We can apply different scenarios to understand how much can we really stress this wind farm and sort of tease the value out of the wind farm, as well as do we have opportunities to introduce new technology and still stay within the loads envelope or the permitting requirements or whatever the constraints are for that particular scenario. So this was just a quote through the Harvard Business Review, but yeah, digital wind farm, digital concepts have huge current value as well as huge potential value for us. Next. And I think that's it. Thank you very much.
Mark, that was great. Thanks very much. I want to be able to control or at least see a wind farm from my smartphone. I think that would be pretty awesome to be able to do that. So we are asking people, if you have a question, please on the web raise your hand so we can unmute you and we can call on you, or you're also welcome to answer it or ask in the chat box. I had one for you, Mark, to start out. Early in your presentation, you had a slide that said that wind availability was 98%. And I'm wondering if you can contrast that for me for other types of energy technologies. So as I take that 98% to mean is that the mechanical availability of a wind turbine is going to be there almost always. Can you give us any sense of how that compares to a natural gas turbine or a coal plant?
You know, I really can't, because I'm a wind guy. I'm a renewable energy guy. Yeah. But in terms of what does availability mean, that means it needs to be available for its duty cycle when the wind comes up.
Yeah. Yeah. Well, that's an amazing figure to me that it's 98%. So. The other question I had is, can you talk a little bit about, you talked about battery storage and some of the tests that you're running on that. How much capability in battery storage are you putting online?
So I work for renewable energy. We have a batteries group, we have a solar group, we have a wind group. When we merge with Alstom in a few weeks, we're going to have all kinds of groups. The combination of wind, solar, batteries at utility scale is coming now. There have been a few hobbyists. I mean, there are less than 10 farms, let's say, that I know of globally where there's really been something, you know, a huge block of batteries and things that has been applied. But so most of the units are selling a storage block for a particular client need. But we are still getting opportunities where we're seriously looking at different battery technologies to blend into a wind farm. And there are opportunities that are going on today.
Great, great. Okay, I am going to go to Bruce Plank. Bruce, I think your phone is unmuted if you want to ask your question.
Sure. Thanks, Amanda. The question is whether small wind machines are also becoming more efficient and able to produce higher capacity factors.
Small wind meaning like
well, anything
900 kilowatts or less?
Yeah, I mean, you were obviously talking about the very large-scale utility farm scale wind machines, and obviously there's a range of size of machines, and I'm curious if there's development at the smaller end along the lines you were talking about, particularly with increased capacity factor, or if that's really limited to the very large utility scale, utility farm size machines.
Yeah, so two parts to my answer. I kind of personally follow small wind, because I think wind at any scale, I want it to succeed. Professionally, I don't follow small wind as much. I have seen articles more in Europe that I would say were not positive articles about community response and different things. I can't answer your question, though, about capacity factors on small wind. However, for large utilities, they need to be sure that any of their power plants are predictable, that they can depend on them, because the buffering that they need to do to blend in these variable resources is important, and I think Steve has got some of that element in his presentation.
Okay, thanks.
So I've got a question from the phone that asks about, you're talking about a lot of the capabilities that wind turbines have and their sophistication. Who do you think is not hearing that message? Because the Wind Center here and then a number of the advocates on the phone are, they want to make sure that people understand the capabilities. So as you're going through your work, who do you find doesn't really understand wind?
The public, unfortunately. I think this is a very niche-y kind of product. Not as much as before. We have had a couple of booms here in the last 5 to 7 years, which has been great. But there is still a lot of misinformation that's posted on the internet. And unfortunately, that's all the public has access to. So that drives me crazy. And I go to schools. I try to educate. I try to, not just drink the GE or Vestas Kool-Aid at all times. These are, I want to be sure that when somebody goes by a wind farm, they go, wow, that is fantastic. I don't want it to be irritating. And there are still articles on the internet that have been recycled for the last 15 years about their bird killers or their whatever this or their whatever that. And that's really just not the case. They don't have a negative house value effect. I've read, it's sort of myth busting, I guess. A lot of that information is something I continue to do.
Okay, great. So I have another question on the web that says there's a lot of severe weather on the plains, and there's been previous history of problems with turbines, blades, and their strength. Is GE doing anything to strengthen the blades themselves against, severe weather and damage to the blades?
So, I've watched, the answer is no, but we already have design standards that we design to, according to our industry standards. There are always going to be extreme events. When a hurricane decides to come through somewhere, it's going to take everything with it. It doesn't matter what you try and put in its way.
Yeah.
I have seen one YouTube video in my 7 years where a tornado actually hit a wind turbine. I saw it pass by several. And so it grabs the blades and it will throw those blades, half a mile, and it'll tumble around and things like that. But no, we can't design blades for Class 1 hurricanes. The probability is actually really, really low, and there really aren't instances where there are threats to people, quite honestly, and that's our biggest concern.
Yep.
Everything else is an insurable event.
Okay, great. I've got two more questions. Are there any community wind farms like the community solar farms we're seeing more and more of?
You don't see those, and I wish we would. The problem is, wind. These wind turbines, they do put out some acoustics, so you don't want to put them near schools. You don't want to put these in the suburbs. They need to be out in the Midwest. They need to be out in these wide open spaces. That's where they belong. The turbines cost, $2 to $3 million a piece. So there's just, communities have a lot of trouble crowdfunding, those types of dollars. And, we have worked with farmers in Iowa, and, we do have some success stories there. We do help with some 10 and 20 megawatt farms. But there's just an economy of scale that goes with this particular industry.
Yeah, makes sense. Okay. Here's our last one. What information is available about degradation rates for wind turbines? The person asked, there's older reports available, but is there any new public data that you could point to?
Yeah, I would. And I'm not researching that, so I don't have a really good answer. Karine may actually have a better answer for that. If I'm looking for public information, I'd probably go to NREL, or I'd probably go to an organization like this that is, purposed to seek out and distribute this type of information. I'd probably start with NREL and derive from there.
Okay, sounds great, because what you have is more private. Okay.
Yeah, yeah, exactly.
Okay, excellent. So we are going to go, and we're going to finish up those questions, and we are going to go to Steve Boyning. Steve is the manager of market operations at Xcel Energy, where he's responsible for wholesale electric market design, renewable energy integration, transmission system open access, generation interconnection, congestion management, as well as congestion hedging. He's the immediate past president of the Utility Variable Generation Integration Group, which is UVIG, and it's a utility forum that brings utilities together to share information on operation and maintenance of wind and solar resources. It's a really great group for the utilities. Steve is also an appointee of the California Independent System Operator Energy Imbalance Market Transitional Committee, so he's helping to plan a system so other utilities can join the energy imbalance market. He has worked for Xcel for 31 years, so we're real pleased to have Steve with us today. And Steve, you can take it away.
Okay, thank you, Amanda. Could we go to the next slide, please? I'm not seeing the next slide.
Yeah, I'm not either. Graham, next slide, please. Okay, hold on just a second. Folks, we were having some problems advancing slides when we started, so just a second.
Ah, there we go. It looked like we jumped two, but that's fine. I'll just jump right in. Oh, there we're back to the outline. I'll talk for a few minutes about the value of wind and then go into some gory details about how we've changed our utility operations in response to the amount of wind that we currently integrate. And then I'll leave some time at the end. So if we could go to the next, we can have Q&A at the end. Some of the value areas that we see for wind resources lie in the environmental responsibility area. Our utility has been ranked by AWEA as the #1 wind energy provider for the last 11 years. We're listed in the Dow Jones Sustainability Index, so we do get some recognition from the industry for the role that we've played as a leader in our environmental responsibilities and in integrating renewable resources in our generation portfolio. I'll talk a little bit about resource planning, one particular aspect of it regarding renewables. I'll talk about it as a hedge against fuel prices, and then some comments about the future. So if we could go on. I think the biggest thing with respect to wind and solar is that it's no longer a special. It's no longer a unique or one-off type resource. It's something that is a competitive wholesale electric supply resource option in its own right. And we integrate them into our portfolio of generation resources in our planning process, just like any other option. And recently we've been seeing wind and solar resources turn out to be the most economical option in their own right, regardless of the state regulations that may be putting renewable portfolio standards obligations onto our utility. So our utility is on track to reduce its emissions 30% from 2005 levels. Currently, you see the stats there on how much of our annual energy obligation for our customers is supplied by wind. We average 15% across all three of our operating companies. Public Service Colorado has 21% of its energy supply in 2014 came from wind resources. And I just think it's funny, I think back in my career in the mid-1980s, our utility, Northern States Power, was putting in 3 100-kilowatt wind turbines in southwestern Minnesota in a town that was named Holland, actually, by the way. But you know, I remember our traditional plant operators saying, you know, it's never gonna succeed. There's no way you could make anything like that fly. So from that 300 kilowatt scenario back then, we now have 5,740,000 kilowatts in our portfolio of owned and contracted resources that we integrate. Let's go on. We have a 20% annual energy, a 30% annual energy portfolio standard for our Minnesota and Colorado utilities. Just forgot to throw that in on the last slide. I did want to talk about the value of wind in the resource planning process. You know, resource planning addresses two somewhat distinct aspects. One is the adequacy of resources, to make sure that enough generation is available at all times in order to meet whatever demand is being imposed on the system by customers. The second value in resource planning is around the cost of the energy that's used to supply those customers. So a lot of times when I've heard people talk about wind resources, I've encountered confusion on the distinction between the resource adequacy value of wind and the energy value of wind. If we had a 100 megawatt wind farm, for example, from the resource adequacy standpoint, we might only count 10 to 15 megawatts of that capability towards our reliability margin, and we might have to procure 85 to 90 megawatts of other type of resource that could be dispatchable in the event the wind wasn't blowing. So that resource adequacy discussion is one value, and because of that discount on the wind resource being able to be there when needed, that's typically not the basis by which wind and solar are selected in our resource plan. Usually what we see is that the value of those resources come just in the energy supply, because they displace fuel that we otherwise would have to burn at a coal or natural gas plant. And that displacement or fuel cost savings combined with the increasing capacity factors, I think Mark mentioned the newer stuff is coming in, he said, above 50%. The higher you can make that number, you not only get the energy value out of it, but the higher that number is, the better the contribution in the resource adequacy component as well. Let's go to the next slide. I wanted to give you this fine print here. I'm not going to read it, and I apologize for the fine print, but I just think the the content of these excerpts from some of our integrated resource plans is of interest to this group. We see hundreds of millions of dollars of savings for our customers over the life of some of these renewable resource additions that we've made at our various operating companies. And that's not even taking into account, in all cases, the fact that there may be costs assigned to CO2 emissions in the future as the Clean Power Plan or other environmental initiatives start ascribing a penalty or a cost associated with carbon emissions in the future. Next slide, please. So with that, I wanted to dive into something to think about in the future. As you integrate higher and higher levels of renewable resources, you get into the situation where there will be curtailments or increasing curtailments of that renewable resource. Just because to drive up the annual average component, a utility has to install more resource than they can necessarily accommodate at all points in time. I had the Mid-Continent ISO in the Midwest has done planning analysis projecting if a utility were to take 80% of their annual energy from wind and solar, how much resource would they have to install? And this was of interest to me because as a regulated utility, I'm used to a dialogue with my state regulators where we look at a prudent level of installed generation capacity to be, you know, traditionally it was in the neighborhood of 15 to 20% above your annual peak demand was the amount of dispatchable fossil or thermal resource that a utility built. If they built more than that, the regulator may have deemed them imprudent. But as we go forward into a renewable future, if we look at 80% annual energy supply from renewables, a utility in the Midwest might install 3 times its peak demand in wind farm nameplate and probably 1 time its peak demand in solar nameplate to get to that 80% annual energy target. And in doing that, there would be probably 3,000 to 4,000 hours a year where there would be some level of curtailment of the renewable resource because there wouldn't be an equal or greater amount of load on the system at the same time. Now that brings me to this slide here where today there's a prevalence of power purchase agreements for renewable resources where the utilities are obliged to take the energy from the renewable resource, or if they have to curtail the renewable resource, pay them anyway. But I think as we look towards this future where there are higher and higher levels of renewable penetration, it really makes the business case for utility ownership of the renewable production asset, because then it can provide the cost recovery on a capital basis instead of a purchased energy basis. And it can be indifferent to the level of marginal curtailments that might take place on the resource. So let's go on and we'll switch gears to operational and system modifications. These are some of the areas that I'll talk about in this section. Let's go on. We have the next, oh, there we go. So probably one of the most fundamental things that has changed with the addition of renewables in our portfolio has been our attention on forecasting. Utilities used to be able to get by just looking at you know, the average temperature profile in their footprint for the next day and some degree of cloud cover estimation, and from that they could predict what their customers' load would be with pretty good accuracy, you know, in the 1 to 3% range of error. What we saw with wind resources as our portfolio grew was that on a day-ahead basis, we were running 16 to 20% mean absolute error in our day-ahead forecast of the wind output. And there's an area of controllable costs that you can manage with better forecasts, and that relates to the backup supply. You may have to commit backup supply, other generators, to address the variability no matter what, but it's that uncertainty that's the controllable cost piece. And if we start a gas turbine this hour because we think the wind is going to drop off, but then it doesn't actually drop off for 2 more hours, and we didn't need that gas turbine. That was a cost our customers had to pay, which we could have managed with a better forecast. And what we've seen is by working on improving our forecast accuracy, and now we're down, I don't mean to brag, but I think we're as good or better as anybody in the industry with a day-ahead mean error of 10 to 12% now. And we estimate that just in this aspect of controllable costs on backup supply, we've saved, like in 2014 alone, probably about $14 million in operating costs. Let's go on to the next slide. Another area where we've seen benefits is the development of regional markets. When utilities pool their dispatch, it increases the number of resources that can respond to variable resource balancing obligations. It also creates a diversity effect, where if I have one unit of variability in one balancing area or utility footprint and a unit of variability in another utility footprint, and I combine them, those two variability effects are not coincident, and so through combination of utility footprints in operations, we get an efficiency saving through a diversity benefit. For those of you that are math geeks, that 1 + 1 = 1.4, that's the same thing as the square root of the sum of the squares. And that's definitely a benefit we've seen in regional markets. So there's another benefit to regional markets too. Oh, thanks. I take that as a notion I should speed up a little bit. We went on to, I have some slides here that are 3 slides on tangent. This is just to give you a brief lecture on the benefits of regional markets, but I tell you what, let's skip that and we can come back to it if there are questions. Can we advance to the slide that says modification bilateral markets?
Steve, this is Amanda. I don't think we meant to speed you up. I think Graham switched the slides, but we're not trying to speed you up. So if you want to, okay. If you want to go back to that slide, let's go back and finish it.
Okay, well, I will try and speed up, though. I notice as I look at the clock, I'm running. So if we can advance 1 from here, the slide that says tangent in the upper corner. Amanda mentioned that I'm helping in the development of the energy imbalance market in the Western Interconnection. I couldn't pass up the opportunity to talk about why regional markets provide benefits. They reduce the cost to transact, and when I talk about transactions here, I mean the wholesale electric market transactions that maintain balance between generation and load. And the need for those type of transactions is emphasized as there are more renewables being brought into the mix, increasing the variability on the generation side of the equation. Let's go on to the next slide. There's one other detail in this cost to transact as well. In the bilateral market areas like we have in the majority of the western U.S. states, there's something called a rate pancake. And for a transaction to occur from one utility to another, there has to be an access charge paid for delivery service on the grid. Let's go to the next slide where that's kind of illustrated. So in this slide we have 3 utilities, A, B, and C. And utility C right now is operating at the highest cost. It's costing them $50 per megawatt hour to produce energy. And systems A and B both have energy that they could sell at those prices, but because they have to pay this grid access charge, system C actually is not going to buy any of that energy, and it's going to forego an efficiency benefit opportunity because of the current structure that we have around grid access and payment for the costs of the grid. And one of the things that regional markets deliver that's a contrast to bilateral markets is this pooling of the dispatch is accompanied with a new transmission tariff design that eliminates these delivery hurdles. And then in a pooled dispatch scenario, system A would be supplying power to system C, and reducing some of their operating costs. So I appreciate you bearing with me as I went off on that tangent, but let's go on to the next slide. In the western states and for our utility in Colorado, we still are in a bilateral market, and we pay these delivery access charges. But one of the things we've done here to improve efficiency with renewable integration is we've established a tariff proposal which is pending at the Federal Energy Regulatory Commission right now. We've established a type of product called flex reserves. And really what we're doing here with this is we're giving third-party renewable developers the opportunity to integrate wind at as good a deal as we provide for our own resources at our own utility. And I would just characterize this as being in contrast to some of the operating practices of other utilities in the Western Interconnection that impose a much higher cost of renewable integration on third-party producers that interconnect to their systems. And they do it because they, I'm trying to think of a diplomatic way to say this, because they say that the reliability requirements they are obliged to maintain are so severe or strict that they have to have these really high costs for integration. In our own experience, we've seen that we can integrate without incurring those high level of costs, and that's what we're attempting to pass through with our flex reserve tariff. So let's go on. Next slide, please. Another area where we've modified our system operations in response to all of the renewable resources is with our dispatchable thermal resource fleet, where we see increased cycling. By that I mean shutting them off and turning them back on, and increased ramping, where we run them up and down from their minimum to maximum operating points. The problem with that on our dispatchable thermal fleet is that increases stress on systems and components inside the plant, and that leads to predictions of increased forced outage rates. So this cycling impact, you may have heard, for those of you that have monitored some of the renewable integration discussions, it's a real concern. And we also have that concern. We've been able to mitigate some of these concerns through projects that improve the control capabilities at our plants, and through increased plant operator training, so that we don't, or that we try and minimize the thermal stresses on the boilers that could occur due to ramping. So just to reiterate, we can mitigate the need for ramping through regional pool dispatch, and when we do have to ramp, we can mitigate through some of these internal measures. Well, let's go on to the last slide in the modifications area. The industry operates under standards, as we all know, and NERC and the NERC regions and other standards organizations establish requirements on the utilities that are mandatory and that can include financial penalties for failure to comply. So getting the rules right with respect to reliability standards is really important to make sure that we have an industry that's accommodating to renewable development. And for example, there's a new standard that's undergoing field trials right now that would relax the burden on utilities to maintain the generation and load balance. If you look back 15, 20 years ago, this utility industry kept very tight regulation on the grid frequency. You know, we were a 60 cycle grid, and of course we still will be going forward. But whereas we might have been 60 with a very minor set of swings around 60 hertz, 60 cycles per second, in the future I think that will relax somewhat, because there's little fundamental reliability reason why the boundary on 60 hertz needs to be so tight. And the field trial that's underway will help relax some of that. And that's good news for renewables by reducing the cost allocation to them for backup and regulating resources. There's some other developments around the NERC Essential Reliability Services. If you Google on that, you'll get more information than you want to read, but it boils down to the ability of renewables to provide ancillary services, things that support the operation of the grid, and in most markets, renewable resources like wind, for example, are excluded from being allowed to even provide those type of services. So there's things the industry can do in standards efforts in those areas to improve the commercial product lines that wind and other renewable resources can participate in. And then lastly, there's something under the NERC standards that I think is a future interesting issue. As wind and solar increases in interconnection, it ties to the electric grid through a DC inverter. And because of this DC connection, it does not provide naturally system support for the frequency at 60 hertz. So this support is sometimes characterized as an inertia response. And there are a lot of technical issues around the inertial response on the system as renewable penetration increases. I think that will be a field of endeavor over the next decade for utility engineers and geeks to participate in. It should be a lot of fun. There's one last thing I forgot to put as a bullet on this slide that folks might be interested in, but there are different standards for a concept that Mark mentioned in his presentation called ride-through. The ability of a renewable resource to stay connected to the grid in response or at the same time to a disturbance that might occur on the grid, say due to a lightning strike or something like that. And right now there's a standard that applies to the distribution system connected utilities. It's called IEEE 1547. In that standard, distribution connected resources are supposed to trip offline. And at the NERC standard level for the bulk electric system, resources are supposed to stay online and ride through. So there's an important industry standards effort underway right now to reconcile these 180-degree conflicting requirements on resources that are interconnected. Might also be an area folks are interested in if they want to pursue the topic further. But I think with that, it takes me to my last slide, and if there are questions, we can talk about that.
Steve, thank you so much. So folks, if you raise your hand, we can unmute your line and we can ask your question, or you can do the little question thing and type in the text box. I've got a couple. The first one is, you had mentioned early on all the work you had done about your forecasting improvements. The question is, were the forecasting improvements mainly software changes, so you're actually seeing wind patterns more, or were there more adapting your operators to respond to information they were receiving?
Oh, that's a fabulous question. The answer is it was the addition, it was an effort in a lot of areas. It was an addition of meteorological inputs into the model, and it was a step away from the National Weather Service model, which is just refreshed every 4 hours, to a model that we worked with the National Center for Atmospheric Research in Boulder. The distinction with their model is it's a continuously updated real-time model, and so it doesn't have this stale data refresh issue that we had with the old National Weather Service model. So between the increased meteorological inputs from all of our wind farms that gave better situational awareness to the NCAR forecasting model, the use of that improved model, and then over time the training of the model. I'm not a neural network programming type person, but I think that that's the software technology that Global Weather Corp is using. They're the vendor that has applied the model that I was just talking about. I think that they've neural net trained it.
Excellent. Okay. So here's one I'm going to read you from the web. It says, is FERC the forum for a multi-utility transmission tariff to reduce hurdle rates? Who would be appropriate entity to bring that kind of case?
Oh, wow. Hey, these are high-quality questions here today, Amanda. ultimately, FERC would be the forum. But just as an example, our utility, Public Service Colorado, is working with other neighboring utilities in Colorado, and we're trying to tackle this on our own to get a design for a multi-utility tariff that's acceptable to the parties, which we would then bring to FERC if we succeed for FERC's approval.
Okay, excellent. Next one, would you describe how Public Service of Colorado control operators, quote, parked, unquote, fossil resources while depending solely on wind for system regulation? And then part two of that is shall wind resources be on AGC, which I think is automatic generation control. So did you get the question?
Yeah, I think so.
Okay.
Parking fossil resources sounds to me like an operating scenario where we have relatively light load and relatively strong winds. And so we take our dispatchable resources that we do not want to fully shut off down to the minimum operating level that they can sustain while remaining online. So to me, that's what parking would mean. If the questioner meant something different, please ask again. But when we have that type of operating condition, it's interesting, but the marginal unit, the one that can vary its output to keep supply and demand balance, becomes the wind resource. And we do have automatic generation control, or AGC, capability installed on about 1,200 megawatts of wind on the PSCO system, which is more than enough for us to regulate during those minimum load type conditions. We've done that on our other systems, and interestingly enough, what we're seeing in the large regional markets is that has now become a required condition of interconnection for large wind resources, is that ability to vary their output in response to a dispatch set point.
So I make sure that people understand when a wind turbine's on automatic generation control, it means that you have the ability to control that turbine just like you would any other generator. That's assuming the wind's blowing and the turbine's online. That's
right. And you know, the preferred operating mode for a renewable resource is take every megawatt you can, because it's every megawatt we take from the renewable resource, we're avoiding burning fuel at a fuel cost in other plants. So the preferred thing is to put them, we call it, at the bottom of the stack, where we take all that's available from them and then use the burning of fuels to fill in the remainder. But when we do have these minimum load conditions where the resources that burn fuels are parked at the bottom, then we have to continue to maintain balance between generation and load by reducing the output of the wind farm. They become the marginal resource.
Right, right. So they're more controllable. So we have 5 minutes left. I've got a number of questions, so I'm going to keep asking. If anybody on the phone has questions also of Mark or of Karin, please let me know and we can ask those as well. Or Mark, if you have questions of Steve or vice versa, let me know. This one, there's a couple around this, so I'm going to kind of combine them. It's around markets. You had talked about all the work and the benefits you see of markets. What is your consideration of joining the energy imbalance market, and then are there other markets you're thinking about joining?
Okay, I can answer that. One of the things that we evaluated in Colorado was whether there was an opportunity for us to interact with our neighbors quickly and relatively cheaply compared to the cost of a large regional market. And the answer to that question was yes. We have two other relatively large utilities that are in our utilities balancing area. They are Platte River Power Authority and Black Hills, Colorado. With those two utilities, we filed at FERC a proposal to create kind of a mini balancing market just inside this footprint in Colorado. FERC responded with some concerns, and those concerns we are reevaluating right now but I do believe we will go ahead and attempt to address FERC's concerns and resume the development of that local dispatch pool. But in the broader context, we're also looking at the other regional options that are available to Public Service Colorado. We certainly have been involved in the development of the energy imbalance market and are monitoring that in order to see whether it would provide benefits to us in Colorado. We have a logistical issue with the energy imbalance market. We have no direct interconnection to it right now. And we would have to evaluate additional costs beyond just the costs of the market in order to assess whether that development would provide benefits for our customers. Beyond the California ISO energy imbalance market, there's another venue to our east is the Southwest Power Pool. There are technical ways that the Southwest Power Pool could be brought into the Western interconnection, even though it currently operates in a separate electric interconnection. And right now we're at the stage, Amanda, of just evaluating the potential for all of those to bring benefits to our customers. We would still need to engage in a dialogue with our regulators before we took any action beyond what we've started already. So time will tell, but we're sure interested.
Great, thank you, Steve. So Mark, if you're available, this question's for you. It said that you assessed a number of technical issues that GE and the wind industry is going to be working on in the future, but they're asking, could you point to a single technical issue that is going to be a key focus to watch for wind development over the next 5 years?
Huh. No, not really.
Okay, so all of the above we'll still be working on.
Yeah, I mean, I just think about the you know, the components of a turbine, and machine heads are in pretty good shape. Rotors are in pretty good shape. Towers are in pretty good shape. No, we're at 98% availability in the industry, so our quality is actually pretty good.
Okay. Steve, is there anything you want to comment on that question? Are there things you're watching for that you see that could be improvements for wind?
Well, one of the things I think is interesting, and it's not in the wind plant itself, but Mark did mention the potential impact of low-cost storage. I do think that would be an amazing development if we could see that. It's certainly something at the utility we're thinking about, you know, the what-if scenarios. And I think there are price points for storage at which, even though you've got efficiency losses because you put some energy into storage, you lose energy when you take it back out. Even with those efficiency losses, there's price points at which it would be economic to install, and that will have a big impact on utility operations. We would see fewer curtailments of the renewable resource output as we get to higher levels of renewables in the portfolio.
Gotcha.
Yeah, no, and I'd agree with Steve. I mean, I think the next frontier is integration of you know, new things, and does that integration create, you know, a feedback problem in some instances? So those are things that we're, you know, definitely looking out for.
Okay. The last question I have is kind of a global one, so it's probably a one to end on, and it says the upper limit for XL for wind penetration was 61%, and I guess that's at some point in time. What do you think is the average energy that could come from wind turbine over the next 5 to 10 years? So I think the questioner is asking about how much could wind provide? Could it provide 50% of your energy, 60%, 80%? So I'd ask Mark the same question, that in the utilities that he works for, what do you think is the upper end for wind penetration, and over what time period?
So I I've seen public studies by different serving areas that say 30% wind penetration is realistic. There is a pathway to that today. I've seen that for the Southwest. I've seen that for the Midwest. I've heard about it in Maui. I mean, lots of different situations where there is a way forward for 30% or more.
Okay. And Steve, how would you answer that question?
Well, I agree with what Mark said. I'd add on to it. We did an analysis with all the utilities in Minnesota last year called the MINRITS, the Minnesota Renewable Integration Transmission Study. We love acronyms. And we looked at 40% and 50% annual energy. As you start getting into those ranges, there can be some inertial or system relay protection problems that could be addressed. And the study didn't have enough time to complete its conclusions with respect to 50%. But we did conclude that at the 40% annual energy level, with modifications to address issues around inertial and short circuit current ratios, that 40% would be achievable. There were transmission upgrades that were necessary too. To get to that level of average energy production, you have to have a grid that can slosh the energy around more so than it can today. But with those modifications, it was feasible.
Excellent. Okay. Well, I want to thank Steve Boyning and Mark Rush and Karen Wadsack from NAU for joining us for this webinar. This has been recorded, and so this will be placed on the Four Corners Wind Resource Center in case you want to go back and review some of the information. Greatly appreciate all of our speakers' time and everybody joining in, and we'll send out a notice when we design the next one. So thank you very much.